Hello everybody, welcome to the office hour. I'm Raffaello Bonghi, technical marketing engineer from NVIDIA, based in Italy for this week. And today we have an exciting episode on the office hour. We are deep in diving on Isaac ROS. In particular, we are speaking about Isaac ROS Teleoperation for robot control. This week we'll demonstrate how to use Isaac ROS Teleoperation to remotely control a Unitree G1 humanoid robot, learn how developers can leverage Isaac ROS to build the teleoperation workflow, stream commands to real robots, and create the foundations for data collection, imitation learning, and next generation of humanoid robotics applications. I hope everybody are start to writing on our chat, ask everything, because this episode is really exciting. And now let me introduce my friends and colleagues, Kajanan and Javier. Hi, my friends. How is it going there? Well, you're in mute, maybe.
Okay.
Yeah.
I think we're good now.
Yes, amazing.
All right. Hey, everybody. My name is Javier. I lead the Isaac ROS team here.
My name is Kajanan, and I'm a software engineer on the Isaac ROS team.
Well, I see something really cool behind you. I'm really curious, and many questions start to coming out from the chat. Can you tell me something more? Let me know.
Yes. We're going to see much more about this robot later on in this live stream. But right behind us, you can see one of our Unitree G1 robots. I think I saw somebody asking for the name of this robot. This is our G1.5 robot, right?
Yep.
And this is it's one of our many robots here in the lab that are all from one of our partners, Unitree. And this robot will eventually be used for showing us some really cool demos towards the middle and later part of the presentation here.
Wow, so cool. And let me know and let me introduce for everybody, because I don't know how many people know Isaac ROS. Please, meanwhile, we'll start to chat, ask many questions, and please reply me if you know what we're speaking about. And yes, meanwhile, if you want to go ahead to speak about Isaac ROS Teleoperation, maybe we can open the presentation. I don't know.
You want the screen share now?
Yeah, let me see. Okay.
Actually, wait, pause. I think he wants to screen share his screen. Pause.
One second. Oh, okay. Let me do it. Okay, see.
Yeah.
No, I don't see your presentation right now.
Okay.
Okay, let me see if it's okay. Now it's live. Let me open. Okay, here we go.
All right. Great. So let's get into Isaac ROS Teleop. So I think Raphael already asked the same question. I'll ask it again. If you're familiar with ROS or Isaac ROS, I would love to see you put some comments in the chat so we can understand how familiar you are with these software platforms. Is anybody familiar with these?
Let's see many people are start to writing. There is usually a small delay between the question we see on our chat, meanwhile they are hearing our live. Meanwhile, we can go ahead, you can speak about Isaac ROS Teleoperation. When we have questions, we can see now. Some people are writing no.
Yeah, all right, that's great. It sounds like we have some beginners or people who are not yet familiar with Isaac ROS. This is a great opportunity then for us to teach you and show you some of the really amazing value that Isaac ROS can deliver. Let's go to the next slide, please. So let's start by defining and reminding ourselves what ROS is. ROS is an acronym. It stands for the Robot Operating System. It's a bit of a misnomer, though, because even though the name has the words operating system inside of it, ROS itself is not actually an operating system. Instead, ROS is a collection of software packages that helps make it very easy to design and build and deploy your robot systems. It's an open source framework. It's a long-running open source project where many developers across the entire world have come together to build and release open source packages that can perform different functions that are relevant to building a robot. For example, in this graph you can see in this slide, you can see there's many different nodes, which are these individual objects connected by these edges, or ROS topics perhaps, that allow you to have some nodes handling perception tasks, understanding what you're seeing in the camera. Other nodes can handle executive behavior, deciding what to do based on the sensor inputs. And then finally, there could be nodes involved in motion planning. How do we take those ideas and turn them into actual motions for our robot arms or other robots to actually execute in the real world? So the overall ROS community is a collection of developers and packages and software and other utilities that help make this graph possible to create and maintain. It's all based on top of the ROS middleware, which is a basic collection of message passing tools so that these different individual nodes can all communicate on a shared language. That allows it to be very easy for you to use modularity and to swap out one node for a different node. Because every node will speak essentially the same language, you can combine, mix and match different parts of different people's ROS package stacks and combine them to make your personal, your computer, or your company's ROS graph for your robot in particular. Let's go to the next slide, please. So one of the things that's really becoming even more obvious as we get into this new age of physical AI is that these next waves of more and more autonomous robots are going to require real-time responsiveness with full awareness of the situation they're finding themselves in. And to achieve that level of real-time responsiveness and complete awareness, we need to really push the boundaries of what's possible with computation and what's possible with algorithms. We need to have really, really great hardware acceleration in our robot computers to allow us to solve these really challenging problems in real time. Next slide, please. This is where NVIDIA Isaac ROS comes in. Isaac ROS is built on the ROS open source platform. It's a collection of NVIDIA CUDA accelerated libraries and AI models that we package and deliver in the form of ROS packages. What this means is that if you are somebody who is already a ROS developer or somebody who wants to become a ROS developer, you can mix and match. You can use NVIDIA Isaac ROS packages to either augment or replace parts of your existing ROS stack. Because we do a really great job of working with these open standards, everything is totally interoperable. And so that allows you to either go from a complete switch or even do a gradual switch where you gradually change or increase the amount of Isaac ROS packages you use. As you can see in this slide, we've got a whole array of different Isaac ROS packages you can leverage. In fact, we have something about 30 different GitHub repositories, all open source code, where you can see different solutions we presented for people like you to go and use in your robots. We also have about 100 or so different packages. Our packages are individual solutions for different parts of the robot problem. So for example, some of our most popular packages include Visual SLAM, Visual Simultaneous Localization and Mapping. And this package uses some of our really amazing NVIDIA libraries to help a robot understand where it is in a scene and to learn about its surroundings. We also have 3D scene reconstruction. You can take the camera feeds from the robot and use that information to build a 3D visualization with actual, three-dimensional voxels that help you understand the surrounding environment. We have solutions for pose estimation as well. If you have a certain object you want to figure out, you want to find the pose of, for example, as we'll see later today, we're going to try to pick up some objects like apples and ketchup bottles and mac and cheese boxes. It can be really useful for your robot arm to know exactly the pose, the three-dimensional, 6-degree of freedom pose of a desired object, so your robot can manipulate and interact with this object. We have other solutions for things like motion planning, object detection, depth segmentation. One of our really cool DNNs that we released for the entire world to use is a DNN for stereo disparity. And so we give you a really great solution to take a stereo camera feed, stereo meaning two cameras side by side, and convert that binocular vision feed into a disparity map and then to learn the depth information from this camera. This is a really great solution if you have a camera like a RealSense camera or maybe a Z camera. Many various cameras from various vendors offer you to get two feeds simultaneously, which you can then use to calculate the depth segmentation. Ultimately, this is all, again, based on the ROS middleware framework. So each of these packages, each of these nodes runs on top of ROS. And underneath the hood, we also work on using many other NVIDIA libraries. So if you're a user of NVIDIA products, you maybe have heard about things like TensorRT, VPI. I hope people have heard about CUDA before. CUDA is one of our really, really core libraries, Argus, and other sensor drivers. We take all these libraries and make sure they're all available to you as ROS packages and ROS nodes. What that means is that if you are somebody who already likes using TensorRT, and now you want to, for example, take a model you've already converted into a TensorRT engine plan, you can then use that same model on your robot as a ROS2 node. And that allows you to very easily transfer from working in a lab or a simulated environment and gradually move that stack into a robot-ready deployment stack. Let's go to the next slide, please. One of the other really amazing advantages of Isaac ROS is this technology that we call Nitrous, the NVIDIA Isaac Transport for ROS. One of the challenges with ROS is that because it's so modular, people tend to design very specific nodes that perform very specific functions. For example, you might imagine an image processing pipeline that goes from a raw camera input all the way to a final detection for an object. That could involve 5, 6, maybe even 7 nodes all in one pipeline. That modularity is great because it gives you the opportunity to customize and choose exactly which solution you'll use for each node. It also makes it very easy for you to fix and modify certain parts. For example, if you have a different camera with a different resolution, you can easily change some of your resizing, or maybe you can change the way you're going to crop on this picture, and ultimately you reuse a lot of the same code, even though you have to make customizations for your particular hardware. However, that modularity has often had a cost. Whenever you have multiple nodes in a pipeline, there has to be a way for nodes to communicate from the first node to the second, second to the third, and so on and so forth. That communication traditionally involves large copies of memory between the first node and the second node. For example, you can imagine an image. An image message has a large array of every single pixel, the RGB values for every single pixel in this image. And you can imagine that large image as being copied multiple times from the first camera node to your first resizing node. You're going to resize the image down. Maybe you'll crop the node the next time. Maybe you'll change it from an RGB to a grayscale image. Each of these operations will involve copying this huge image over and over and over again. And that's very expensive and very slow. Thankfully, NVIDIA has a solution for this. NVIDIA's Nitrous solution allows you to avoid copying back and forth from CPU to GPU whenever possible. So this animation here you can see on the right side of the slide, this animation demonstrates how NVIDIA Nitrous works. On the bottom half of this animation, you'll notice that when that first message comes in from the left side, right about now, that message is initially copied to the GPU. And then that data stays on the GPU for the duration of the Nitrous pipeline. On the CPU side, we can keep a simple ticket or a simple pointer that helps us keep track of this message, but we don't have to copy that complete memory buffer back and forth between CPU and GPU. If you look at the top part of this animation, you'll notice there's a lot of copying going back and forth. The same image has to go up and down multiple times for the duration of this pipeline. But thanks to Nitrous, we can really avoid that. One of the great things about Nitrous is that even though it is a specific technology invented by NVIDIA, it still uses open source standards for ROS. So if you are combining Nitrous NVIDIA Isaac ROS nodes with other non-Isaac ROS nodes, for example, some open source nodes from the ROS build farm or from some other person you found on GitHub, those nodes are still fully compatible. Whenever we have to, we will simply send you a CPU message, a regular normal ROS message to any regular normal ROS node. That allows you to get the full benefits of Isaac ROS whenever possible, but we're still compatible when necessary. And these technologies are available to you right now. If you are interested in if you're somebody who wants to write your own Nitrous-enabled nodes, we offer many technologies, including CUDA with Nitrous, Nitrous Bridge, and PyNitrous to help you, as a package author, write your own custom ROS2 node that still gets the benefit of NVIDIA's technology for Nitrous here. In fact, one more thing I'll mention right now. NVIDIA works really hard and works really, really well with the Open Source Robotics Foundation and the larger open source robotics community. As part of that collaboration, we've actually worked to contribute a brand new feature to the newly released ROS2 Lyrical release. This is the brand new ROS2 release for the overall ROS2 community. And that new release has a new feature called the ROS IDL buffer. This new technology allows anybody to use some of the same core technology as Nitrous. In fact, we've actually kind of contributed this Nitrous technology over to the open source world. And so now you could be using any hardware accelerator, any GPU, any device you like, and you can write customized software that can benefit from the same exact technology that we're using here in Nitrous. So at NVIDIA Isaac ROS, we put a really big emphasis on working with the community to make sure all of our great solutions are available for the whole community to use. Next slide, please. So as I mentioned before, there's a whole array of different libraries and technologies that all exist in the NVIDIA Isaac ROS platform. And I'll mention again, it's all open source. It's almost all open source. It's all on GitHub. You can find it on our GitHub right now. You can go through our GitHub documentation. You can clone the repositories. You can build them from source. If you want to, we give you Debian packages that are pre-built, so you can save some time. You can install the pre-built applications. And it's our job to make sure you have the total universe of Isaac software, amazing Isaac software, NVIDIA goodness that you can use for your robot applications. In particular today, we're going to be focusing on teleoperation, which my colleague will talk about in a little bit. But we want to make sure you understand there's a really, really big ecosystem of Isaac ROS packages out there for you to take. Let's pause here for some questions and see if anybody has any interesting questions we should answer. Raphael, you want to give us any questions that are worth flagging?
Yeah, there are some questions meanwhile. This subject is really appreciated for the community. I start some question. Let me start in order. Okay. This is the first one. Do you see? From a LinkedIn user that is following from LinkedIn. As a humanoid robotics move towards foundation models, what type of teleoperation data have proven most valuable for closing the sim-to-real gap? And where do you still see the biggest limitation today?
Yeah, that's a great question. It's a very big question. It's a big question with a complicated answer. I'll give you a simple answer right now. And of course, this is definitely an open area of exploration. It's an open area of research for NVIDIA. And so we're still trying to find the best solutions here. But ultimately, we believe in the idea of a data pyramid. So you can imagine a data pyramid is a situation where we have a small amount of really, really high quality data, a larger amount of maybe less medium quality data, and a very, very large amount of perhaps low quality data, the data where there's less signal, less information for us to learn from. And so a lot of our approaches are going to involve using every possible kind of data at the various levels of fidelity, and to then communicate that information and turn that into a really great foundation model. So ultimately, for our teleoperation demos, we often use technologies like XR headsets. In fact, later today, we're going to show you a demonstration using a Pico 4 Ultra headset. That's one of the classic VR headsets that are very popular. And other headsets like that are really popular and really commonly used for our teleoperation data collection. Let's go to the next question.
Yeah, sure. Yeah, thank you for the first reply. Let's move to the second one from the LinkedIn user. For engineers preparing for the next wave of physical AI, what technical skills will you prioritize today? ROS2, reinforcement learning, simulation controls, computer vision, or something else entirely?
Yeah, the easy answer is all the above. You know, robotics is a very full stack problem. It involves thinking about every possible element of the robotics stack, think about the complete system, all the parts. And importantly, because it's a very integrated problem, and we have to push the very frontier of what's possible on hardware and possible in software. What that means is that we need people with every possible background, every possible experience, every possible expertise to help us find that limit, to find the boundary, and really push us towards that limit. So ultimately, all these topics you mentioned are all really, really important components of a complete robotic solution.
Wow. Well, there is now another interesting question, in this case coming from Maverick from YouTube. We found some really interesting feature like the real sense processing that is really a step forward on Isaac ROS, while some components like nav2 looks like pretty the same. I'm missing something?
No, I think you have a good summary of the understanding. So NVIDIA tries to make sure we focus our efforts on the particular areas where we can make a really big improvement. So when we discover there's an opportunity to really push the boundaries of what hardware and software can do, then we will tend to focus our efforts on building those solutions out really well. So we are really big users of nav2. We like nav2 a lot. And so the nav2 solution that's already out there is already a really great solution. And so we're happy to work with open source solutions that are already out there whenever they're possible. We try to focus our effort on where we think we can provide the most value. And often that means focusing on really particular libraries or applications where NVIDIA has deep domain expertise and also really great hardware to match.
Thank you. Let's move. Maverick is also wrote the following message, like maybe an alternative native nav2 system on Isaac ROS that we are not aware of, I think. We see tutorial to use cameras for perception, but not SLAM, but is our primary navigation source.
Yeah, so I think, the first part of your question, I think we answered already, but the second part I'll mention, one of our SLAM packages, you'll see it on the slide, actually we saw it a little bit earlier, but we have a visual SLAM solution. So visual SLAM means using camera data to perform SLAM. I think many engineers have traditionally thought about SLAM from a LiDAR sense. You can imagine a simple, two-dimensional spinning LiDAR on top of your robot, the very classic, Waymo or other robots with a very similar form factor. And that's a great solution for some environments. But for other environments, we think the visual SLAM approach is actually really, really great. We can use the cameras to get a large number of really high quality features, and we can track very chaotic scenes pretty well thanks to the amazing fidelity of a camera sensor. Yeah.
Well,
Okay.
Many other questions I see now from YouTube.
Yeah, I
This
want
is
to make
really
back to the slides too. I want to we don't run out of time here. I think let's pause this. Let's do this last question right now, and then we'll go back to our slides for the rest and come back to questions toward the end as well. Does that make sense to you?
Yeah. Which question are you speaking about?
The one you have right now is great. We'll answer this one right now. So the open source tutorials. That's a great question. Yeah. So the Isaac ROS documentation, which I'll put a link to in the chat at some point, but the Isaac ROS documentation exists to help you use Isaac ROS software. Now, we are not offering a direct course that immediately explains to you, robotics fundamentals from a 101 level all the way up, but there are many really great resources available to you online. And in fact, if you're interested in more of a complete course, NVIDIA offers some DLI courses, the Deep Learning Institute. So you can take these courses, you can actually pay to get a certificate for this course to prove you've learned this knowledge from the course. There's a test, an exam at the end. And these DLI courses can be a really great way for you to get more of an experience and understand from the foundations of robotics all the way up to actually using Isaac ROS in real application. So our open source documents that are on the website are more focused on using Isaac ROS, but if you want to learn more about the robotics system as a whole, then the DLI courses are a great way to get that.
Thank you. Well, not only thank you from my side, but also I read a message.
Appreciate that. Yeah. Let's go back.
Let's go ahead. Yes, let's move here. Yes.
Yeah. So we're going to talk a little bit more quickly about teleoperation in particular. So as I hope you're all are aware, the goal of today's workshop and this demonstration is going to be to focus really on teleoperation. So let's talk about what teleoperation is and why it's important. So teleoperation refers to the idea of having a human operator, somebody like me, using a device like a VR headset, for example, this one, and then use that device to collect information from the human operator that we can then use to teach on the robot right there. So, for example, in a humanoid robot situation, the humanoid robot has roughly a similar morphology, a similar body structure to what a human has as well. Similar, a pair of arms and a pair of hands in each arm, and these hands are, roughly speaking, mapped to a human hand. And so, if I want to teach the robot how to pick up an apple or put an apple onto a plate, I could use my own knowledge as a human. I'm pretty good at picking up apples as a human, so I can practice that motion in the VR headset, collect the data, and use that data to help improve and train the robot models to get better and better at tasks like this one. So, in particular, teleoperation is a great way to get really, really high quality data that is as close as possible to what the robot will see in the real world. We have many other applications, other ways to collect data as well. For example, you could train on some videos of people interacting with objects. You can also train in simulation, but training in the physical, real robot with a real operator and a real robot picking up real objects, that can be a really great way to get very high fidelity information about the task. And that's why teleoperation is such an important component of the overall data collection system. Let's talk a little bit more about Isaac ROS Teleop and how that package works. So Isaac ROS Teleop is the Isaac ROS wrapper based on the core Isaac Teleop library. Isaac Teleop is a framework for really high fidelity, egocentric, and robot data collection. Egocentric means from the perspective of a human operator, like from a single person sitting in a chair looking outwards. One of the great features of this framework is that we have done a great job to unify many, many different hardware vendors and their solutions into one simple interface. What that means is that as new vendors work with us, new partners work with us, for example, to add new headsets or new motion capture technologies or even new robots, we can connect all of these and make them available to you, our customers, our users, as a really simple single interface. And that way you can continue to benefit from the amazing new developments that are happening in the hardware world and the software world, while still keeping your life simple as a developer who wants to integrate Isaac ROS technologies or Isaac Teleop technologies into your robot stack. In particular, we're going to focus on the single headset today, the Pico 4 Ultra. But of course, there are many other headsets that Isaac Teleop supports, and the number of supported headsets will continue to increase as time continues. I want to talk a little bit more about our Isaac ROS physical AI stack as a whole. So teleoperation is simply one portion of the stack. Teleoperation helps you collect the data, understand what the human is seeing and doing. But then the next question is, how do you translate the data and convert that into the actual robot joint angles or robot targets for the physical robot to create? We provide to you a whole list of packages. They're all on our GitHub in open source code for you to use. And these packages are specifically tied to the Unitree G1 robot right now. So we are using a G1 robot as our first, simple platform that you can work with. And this platform will leverage a couple of different technologies from NVIDIA to make the whole thing work. First of all, we use the NVIDIA's Agile Whole Body Control Policy. This is a learned network that helps us translate and understand how to move every single joint on the robot's body. As you can probably tell, the robot has a lot of different joints. There's a knee joint, there's ankle joints, hip joints. All these joints have to be correctly controlled for the robot to maintain stability and to move around in life. We also need to make sure that we can combine the headset information, the hand pose information the human operators can provide, and map them to the robot hand poses as well. Even though the human has, a similar morphology, it's not exactly the same morphology. So, for example, if I have my hand in front of me, it's possible that the angle of my elbow and the angle of my shoulder will not be the exact same angle the robot has to maintain. Thankfully, NVIDIA has a really great library called cuMotion. cuMotion is our library that helps perform inverse kinematics, so we can take our target pose, our 6-degree freedom pose of the robot hand position, and then we can calculate using our library what the exact angles must be for every single part of the robot arm to achieve the target pose here in the robot frame. So together, cuMotion, Agile, and our teleoperation stack all work together with the open source ROS2 control middleware framework to allow us to get a full end-to-end stack running on the G1, as we'll see shortly. Okay, I think we're done with the discussion and kind of overview of the slides. Should we start our demo now? What do you think?
Yep, so now we'll be going over the demo. So Javier will be acting as our teleoperator. So just
One
to
second
go
that we rearrange the live to show also the lab, I think.
Oh, right. Yeah, you can show lab view now.
Yes, perfect.
Screen view
now can we go back?
Okay.
Yep. Now can we go back to screen view so that we can go over the documentation and show how to.
Okay. This view?
Yeah, this is great.
Yep.
Perfect. Okay.
So Javier will be acting as a teleoperator. He'll be using the Pico headset over here, which he'll be connecting onto the robot. And the robot we're using is the Unitree G1, which has a Thor connected to it through the Thor backpack. We'll discuss the details a bit later. So I'll be giving him the headset and the controller, and then I'll be walking us through the documentation for how to actually run this and teleoperate the robot.
Hold on. Okay.
All right. Let me get this.
I'm finding the best way to show the documentation and the robot at the same time.
I think we're going to screen share on his laptop, actually. So don't worry, Raffaello. We have it on our side. Right.
So to start off, yep, you can go.
Thank you.
So to start off, I'll be going over the getting started section. So this is roughly what you have to do to get started on the Isaac ROS platform. And this is common between all our packages. And so we try to make the setup as easy as possible. For this demo, we've already pre-done it. So everything's already set up, but I'll be just going over these steps quickly just to ensure that everyone's aware of what we did beforehand. So first, we checked the platforms that we support. In this case, we're running it on the Jetson Thor specifically. That's, as I mentioned before, connected to our Unitree G1. It is running on Jetpack 7.1, and it has an SSD connected to it. And we've also configured the power settings accordingly. So now we'll be going on to ROS support. So one thing to note is Isaac ROS is currently on ROS 2 Jazzy, which is, I believe, the release from last year. Eventually, Lyrical just came out, so we will be eventually transitioning to that, timeline pending. But for now, we're on Jazzy. And so the next step is to initialize our compute. So in this case, we are on the Jetson platform. So I select Jetson platform here. And then we basically went to this URL over here, which is the quick start guide for flashing the Thor. And then we flash the Thor offline. This process takes quite some time, and so we decided to do this offline. But roughly what this does is just gets you an Ubuntu image onto your on your Thor with Jetpack 7.1 so that you can run the stack. Following this, what we did was we installed some necessary components that we needed for Jetpack. Some of these include CUDA, Docker, and other things like that. And we roughly just ran these two commands. But again, I won't be going over the details just because this is initial setup. Following that, we just double checked that we installed the correct Jetpack version quickly, and also did some other setups, such as setting up the Jetson onto max end mode, which allows us to overclock the Jetson so that we get maximum performance. And these were done through these two tutorials. Following this, we created an Isaac ROS workspace. In my case, we roughly just make the directory called Isaac ROS dev, and then we exported this Isaac ROS workspace environment variable, which points to this workspace, and then we sourced it, and this just creates us a directory with the Isaac ROS workspace. After this, what we did was we installed something called Isaac ROS CLI, which is a wrapper to simplify the setup of Isaac ROS. So in this case, once again, we just ran through some installation steps. So we set the local in our system to UTF-8, then we installed some dependencies, and finally we pinned to release 4.4, which is the latest version of Isaac ROS currently. And then after that, we selected Docker mode, and this is just so that we had an isolated environment for this demonstration. So we decided to use Docker mode. And then after that, we installed Isaac ROS CLI. And then we completed the Jetson Thor platform Docker setup, and then essentially just initialized everything so that we could use Docker. One thing I'd like to call out is if you'd like to customize your Isaac ROS environment further, we do have some tutorials over that. But in this case, we just use the base image. And so this is just an initial setup just for the environment. And once again, we did this beforehand. Now we'll be going over the actual demonstration. So in this case, I went to repositories and packages. Following that, I went to Isaac ROS Physical AI. And then I went to Isaac ROS Unitree G1 Teleop. So this tutorial is what we use to go through the setup of setting up the G1 with the VR headset and other things like that. So this is roughly the tutorial we did it. In this case, as I mentioned before, we're running this on an AGX Thor. We have a Pico 4 Ultra connected, which Javier is connected to. And for that Pico 4 Ultra, it's currently connected onto the same network as our robot. So the Thor and the Pico headset are on the same network. And this is just so that they can communicate with each other. Following that, we also obviously have a Unitree G1 that's powered on. And in addition to that, our host machine, in this case, the Thor, is connected to our Unitree G1 through an Ethernet cable. So after that, we already went through the setup development environment roughly, just in the getting started section that I went over briefly. After that, what you should do is basically set up the G1 with the Jetson AGX Thor connected to it. So Unitree provides 2 documentation links to do that setup. We won't be going over the setup since our focus on this case is just on the actual teleoperation demo. But you can look at these 2 pages to understand how we actually set up the G1. One thing I'd like to call out in particular is our specific G1 uses something called the Thor backpack. And this is mentioned here. And so to purchase your own Thor backpack, the recommendation is to contact Unitree. But if you don't want to use a Thor backpack, you can also just connect it through Ethernet and then use it that way. In addition to that, there's the quick development tutorial. And this is what we did roughly to set up the Unitree G1 for us to use with the Thor, such as going through network setup and other things like that. And so you can see here, this is the IP address of the robot, which we'll be using later. So the next thing we did, which is also something we did beforehand, was we essentially created an Isaac ROS Docker argument. And this was done by creating a temporary folder called in our home directory called .cloudxr, which we'll discuss a bit about later. And then we roughly just mounted this onto, we added a Docker element onto our home directory .isaac ROS dev -docker args to essentially tell Isaac ROS's Docker container, hey, let's mount this container onto this directory onto our container. And so this is all that does. Just to show you how that looks like, this is my terminal. And if I go on to terminal 3, you can see if I cat this .isaac ROS dev docker args, you can see roughly what it looks like is just it's giving Docker the -v for the volume mount command and telling it to mount the Unitree's .cloudxr onto our Docker container. After this, what we did was we installed and built Isaac ROS. In this case, what we decided to do was do the binary package. So what we ran was first we ran Isaac ROS activate, and then we ran sudo apt update, and then sudo apt install -y ROS Jazzy Isaac ROS Unitree G1 Teleop bring up. And we just ran this on the first terminal, which is already inside our Isaac ROS environment. So we ran this command, and then that essentially just installed the G1 Teleop bring up. But we've done this beforehand just to save us time to avoid the installation process. We also installed ROS2 Jazzy Majoko ROS2 control just to use some packages within this. But the details here are not that too important. We just roughly copied this, and then we ran it in terminal 1. And then that gave us access to these packages as well. So this is how we did this initial environment. Following this, we need to run something called CloudXR. So CloudXR is something within Isaac Teleop that allows you to connect the VR headset to the Thor. Essentially, what we're going to be doing is running CloudXR as a server on the Thor, and then the headset will be acting as a client that then connects to that server. So the first step for what we did was we first CD'd to our Isaac ROS workspace, and then we cloned Isaac ROS Teleop, and this was done in terminal number 2. So you can see here, if I CD to Isaac ROS workspace as source, I already have Isaac ROS Teleop installed. So as a result of that, I cloned. So as a result of that, I won't be recloning the Isaac ROS Teleop. After this, what we did was we ran this command, and what this does is essentially starts the CloudXR Docker container, which runs the server for the headset to connect to. And so now I'll be running this command. And then I will be running it. And now you can see we started a Docker container, and now you can see that the CloudXR runtime service has started. And so now this will enable a user such as JVR to connect to the headset. So now we will be following the connect the XR headset to the Teleop guide. So we'll be clicking here. And then we'll be following this tutorial on the Isaac Teleop documentation. Since we're using a a Pico 4 headset, we'll just be following this tutorial. So to start off, what JVR did was he opened a web browser, and then he went to nvidia.github.io/Isaac Teleop/client to open the web browser. Now I'll be switching to JVR's view to see the actual screencast. So this is with the headset open. JVR has connected to it. So now he will first be choosing the Teleop application. So in this case, he selected Isaac ROS as the Teleop application to use. So he clicked that, and now he's on that. The next thing he did was we went to the server IP, and then we determined what the server IP of our Jetson was. And the way we did this was by going to our Jetson. So in this case, I'll be going on terminal number 3 on our Jetson and typing ifconfig, and then looking for which IP address is our IP for our Jetson. And in this case, it's 10.137.144.218. So JVR went and typed that as our server IP. And so now we have that connected. The next thing JVR will be doing now is accepting the cert. So what he'll be doing is clicking accept cert, then going to advanced, and proceed to accept it. Now he's accepted it. So now he can exit this tab and proceed onto going down. And then the last thing we have to do is change the video codec to H.264 streaming. And this is just a more efficient streaming that enables you to use the Thor. It's just essentially a compressed image so that you can stream from the headset better. And so he set that, and now he's ready to actually connect to the server. So he clicks the big connect button. So if he clicks it, you can see now, give it a second. You can see now that this is sort of his view. So you can see that the status is connected. This means he has successfully connected the headset onto the Thor. And so now this is sort of what he's seeing from the headset. So now what we will be doing is we will be actually running this on the real robot. So the first thing we'll be doing is changing this tab into real robot. And as some safety cautions, obviously working with the real robot can be dangerous. So some recommendations we have are, make sure that there are no humans in the working area. Make sure you have a human holding the robot up if you're using a gantry, just because a humanoid robot can fall over, and that's not a good thing if it hits someone or falls down, and it could break. In terms of our stack, we recommend always starting with a blend ratio of 0.0 and then increasing that to 1.0 gradually. And the reason for this is just so that if the robot starts freaking out, you can quickly just set it back to 0 for safety. We also recommend setting the waist yaw joint position of the robot to roughly 0. And this is because we don't control the waist of the robot. And so if it's not set to 0, it's possible that the robot can have degraded performance with the whole body controller and can fall over. So for safety purposes, rather than having the robot like this, we recommend just having it pointing straight, essentially. And then the final recommendation is we always recommend having the disable command ready. And this is just in case the robot freaks out. You can go ahead and stop it from doing anything crazy, just for safety purposes. In addition to this, we always recommend running everything on a separate ROS domain ID. And the reason for this is because if everything's on a separate ROS domain ID, then you'll be isolated from other people potentially working on robots. And so you won't have crosstalk between multiple robots, which could lead to unsafe behavior. So that's just a quick note about safety. The next thing to do is set up the network. So our recommendation is to run Isaac ROS robots. And then outside of our Docker container on the host, you will run the network setup script. I've already cloned the repository, so I won't be doing that part. But now I'll be running the network setup script. And this will be done on terminal number 3. So I roughly just copy and pasted that, and then just ran this. And then you can see that this will let us set up the network. In this case, we're using a Unitree G1. So I will be selecting robot type 1. And I'll be inputting the password of the Unitree, which I won't share, obviously, because it's our password. And now finally, you can see that we have these network interfaces up. We have already set up our network interface, so I won't be running the full setup once again. But you can see here that the IP of our Unitree is 192.168.123.99. And then that means the correct network interface for us will be 192.168.123.166. And this corresponds to network interface ENP2P1S0. So in order to communicate with the robot, this will be the network interface that we use. So I'll be copying this just for use for later. But I won't be running the entire command just because we've already done this. But roughly, once you select the network interface, this will just set the network between the robot and the door. So now that the network is set up, the next thing to do is to actually launch the application. So once again, in terminal number 3, I will first set a ROS domain ID. In this case, our ROS domain ID will be set to 63, just as a random number. And so this will prevent ROS crosstalk. And just to confirm, I'll be running ROS2 topic list. And you can see the only 2 topics I can see are parameter events and ROS out, which to me implies that no one else is using this ROS domain ID. So I know it's safe to use. After this now, I will be launching the application. So I'll be copying and pasting this command. Roughly what this will do is run the full stack that Javier talked about before. So we'll be using various NVIDIA technologies to run this. Q-motion to control the upper body to get positions for where the hand should go. Agile for the lower body so that the robot can walk around and stuff. In addition, we'll be using the teleoperation to actually control the robot. So this launch file runs all of that, the entire stack that Javier talked about before. So now I copied this, and we'll run this here. And in addition to this, from the previous step, I got the network interface as ENP2P1S0. So I'll be copying this and changing the network interface to that. So now I have the stack running, and now I wait a while just for everything to launch. So I'll be waiting a bit. So it takes some time to launch, but hopefully we will see it soon. In addition to that, I'll continue moving on. So one thing to note is that once you start this launch file, the robot actually won't move. And this goes back to the blend ratio thing we talked about before. Roughly what the blend ratio does is when it's set to 0.0, then the robot is just set to essentially a safety controller that doesn't enable it to move. But as you increase it to 1.0, it relies more and more on true motion and agile to actually run commands. So now we can see that the stack is running, and you can see that the IK controller is running. So Terminal 1 currently has the full stack running. Terminal 2 has Cloud XR running. And now finally we're in Terminal 3. So inside Terminal 3, I will be running Isaac ROS Activate. And this enables us to re-enter the Isaac ROS environment. The next thing I will be doing is setting our ROS domain ID. So I previously set our ROS domain ID to 63. So I will be doing the same thing. And just to confirm, I will be running ROS2 topic list. And you can see, I can see a bunch of various different topics. And these topics correspond to what the stack expects. Now what I will be doing is just confirming that the teleoperation stack is running. So the way I can do this is by running ROS2 topic echo / extra teleop / EE poses. And what this topic corresponds to are the actual positions of Javier's hands relative to himself. So when he moves around, you will be seeing this updating. Now what I will be doing is setting the safety blend ratio to 0.0. And this is just done, again, for safety purposes. And this will also be our disable command. So if something goes wrong, I will quickly set this back to 0.0 so that nothing unsafe happens. Now what I will be doing is actually setting this to 1.0. So now I think we can set this to lab view so that we can see the lab. And all I'll be doing is hitting enter with this command. So right now I'll be running ROS2 param set / safety controller blend ratio 1.0. And now what we expect to see is the robot will start to move. So you can see now if Javier moves his hands, I think our stream might have, okay, never mind. So if Javier moves his hands, or he's moving the controllers right now, I guess, you can see the robot itself will be moving. But if he moves his hands, you can see the robot follows his hands. So essentially, he is now controlling the robot using his VR headset. The stream seems to be freezing sometimes on my end, but hopefully things are okay. So now what Javier will be doing is he will be trying to pick up an apple and placing it on the plate. So let's see if he can succeed on this. Yeah. One disclosure Javier wants us to point out is he is a software engineer and not a professional teleoperator, so expect some mistakes when he's doing this, but hopefully he gets it on his first try.
It's so cool to see this robot in action. Isaac ROS Teleoperation live is amazing.
So you can see he picked up the apple, and then he moved a bit to the left, and now he is placing it down. And you can see he successfully did it. Now he's doing a little happy dance to celebrate that he was able to teleoperate the robot. Also, one thing to note is in terms of controls, to move the robot left and right and up and down, he's been using the left joystick. To rotate the robot, he's been using the right joystick. And then obviously for the actual hand tracking, he's just been moving his hands up and down, and it's been tracking that. So now Javier seems to be keen on trying a harder object. So I think he'll be trying to pick up the ketchup bottle next and seeing if he can do that. I think the network is freezing. Okay, never mind, we're good now. So yeah, keep going. One thing to note is this object is a lot harder to grasp using the tri-hand gripper. So the way this gripper works roughly is he, oh, actually picked it up, never mind.
Made it. It's here, the ketchup. Apple with ketchup, I don't know the taste, but sure. It's a good job from Javier.
Yeah, so it'd be an amazing dinner or lunch. Okay.
Yeah, yay! It's really incredible.
Do you want to do the mac and cheese box as well, or shall we call it?
Well, let's see from the people. What do you want to see? Another one, or maybe it's better to reply the question now. And by the way, thank you, Javier. Yeah, it's amazing to see. We don't have a lot of time, by the way. I was looking now the time, and we have many questions. Exactly. We can go to the chat meanwhile. And thank you really for this live. Be honest, I would like to see the last one, but it's not the time. He's really a great teleoperator.
So now we'll be showing how to actually disable the robot. So if you go back to my slides.
Yes, we are already back.
What I'm doing is I'm setting the safety blend ratio to 0.0, and this will disable the robot. So now if you can go back to lab view, just to show how that kind of looks.
Yes, 1 second. Here we go. Now we're live view. Okay.
So now I'm hitting enter, and now you can see the robot gets disabled. I guess that was a bit.
No.
But it's okay. Nothing bad happened, and now the robot is safe to disconnect. So now I'll be killing the first terminal, which is the actual robot stack.
One second. Let me jump to the.
Oh.
Okay. Now I can show your terminal. Okay.
Yep. All I ran was Control-C to kill the stack, and now I'm killing the Cloud XR server. So I press Control-C here as well, and now this is down as well. I guess it's taking a bit of time. I'll press it again.
He's tired. This is the reason.
Yep, so it worked the second time. So now the full stack is done. So now it's safe for Javier to remove his headset and remove the controllers and come join me again so that we can answer some questions or any comments that
he's coming back.
Yep.
We can see him coming.
Pause for his amazing teleoperation.
Thank you very much.
I was surprised you got the ketchup bottle on first try.
Yes, people are asking about apple with ketchup. I hope not to eat today. Just to move.
Not a combination, but a very exciting dexterity challenge for a robot. Yeah, so great work done on running the whole demo. It was, from my perspective, it's very easy as the operator. I just put the headset on. I can control the joystick very naturally. And obviously, it's amazing code running behind the scenes on our Jetson Thor computer to help us actually control and go from these really simple inputs, these video game controller inputs, the thumbsticks on the joystick that's a video game, and you can convert those amazing simple inputs into really, really awesome outputs on the robot. So it's all part of the magic of the NVIDIA Isaac ROS physical AI stack.
In addition, I'd like to point out that this is all released today open source. So you can give this a try if you have a Unitree G1 available. The setup is there, and if there are any issues, feel free to file GitHub issues and we'll respond as soon as we can with hopeful fixes, but hopefully it'll be easy.
Yeah. Some questions.
Where we are here, sorry, I made some. Meanwhile, we have some questions that I would like to reply quickly because the time is flying. Let me open, let me also remove, the robot, the laboratory view. And let's start from this question from YouTube, from FTA Netty. Yeah. It is computed with already Isaac ROS nodes and developments. Well, the reply is quick. And there are way to check release compatibility nodes or something similar.
Yeah, so I'll put a link. I'm not sure how I can easily send this to you right now. Maybe I'll see if I can put it in the live chat, perhaps. But
yeah, meanwhile, we are sharing some links already. Just to...
Yeah, I put a link to our release notes. So first of all, the first question is very easy to answer. Yeah, exactly. We already do support ROS 2 Jazzy, and everything else is in ROS 2 Jazzy already. So the Isaac ROS 4.4 release, which is our latest release, is built in support for ROS 2 Jazzy, the open source framework. And so any existing ROS 2 Jazzy node or package you have from your other software stack should be able to play just nicely together with the Isaac ROS stack as well. Yeah.
I see another interesting question. Let me jump directly on question. Javier, would this technique include a body pose model to collect joint positions?
That's my colleague, actually. Go ahead.
Yeah, so currently we don't actually track the body pose, unfortunately. So we only track the end effector controllers. This would have to be a feature that would have to look to in the future to support within Isaac ROS. I don't remember if Isaac Teleop supports this, unfortunately, so you have to double check the documentation, but currently we don't track the body pose. We only track the end effector positions from the controllers.
There is another question. Let me open this one from the LinkedIn user. What is the achievable accuracy of the joint target during teleoperation on a real robot? Is it fully body robot telecontrol supported, or is the solution limited to the upper body manipulation tasks?
So for the achievable accuracy, I think it would have to be staying tuned to see the performance of how fine-tuning goes. I don't know if we can discuss our timeline.
No, so I think I'll mention one thing, right? So the first part of the question, it sounds like how well can the robot match the poses input by the human? And the answer to that question, I think, is I don't know the exact numbers, but I would say very well, right? So we have a really great target. So as long as the human arm hand poses are within a achievable position, achievable pose for the robot arm, thanks to our commotion solver, can get really, really, really close, almost perfectly exactly to the position on the robot side as well. Of course, this is only talking about the teleoperation side of the equation, where you're having a human operator directly controlling the robot. When you want to go from beyond teleoperation to then collect data and train a policy, then that question can be a much more variable question. It depends on how good your data is, how long you train it for, and how well that robot stack runs in the real time. So that's a secondary question, which we'll definitely have more developments on in the near future.
As for the full body robot teleoperation versus upper body, so Javier was able to control the lower body using his like the controller, but obviously if you want to like have the robot like kick or something like that, that's not something we currently support. So you can't control the the lower body itself to like go up currently. It's only upper body for actual teleoperation. The lower body is only controlled through joystick commands.
There is another question coming. Well, let me jump to this question from YouTube. What limitation will you have with this demo if you use the regular NVIDIA Orin instead of an NVIDIA Tor?
It's a great question. I'll answer it in two parts. So first of all, right now, our Isaac ROS 4.4 release, the latest release that we've made public so far, only supports the NVIDIA Thor series of models, series of jetsons. However, anybody who's been following the news, you'll maybe hear that the NVIDIA Jetpack team has been working really, really hard to release a brand new version of Jetpack coming very soon, the Jetpack 7.2 release, which upgrades the older Orin family to start supporting the newest generation of NVIDIA software. And so in the near future, we expect to also start supporting the older Orin series on our latest NVIDIA Isaac ROS teleoperation stack. Right now, unfortunately, it's not supported. Another constraint, of course, is that when you run a teleoperation stack, in particular, if you want to run a whole body control, in the sense that you want to have some inputs from the human combined with other inputs from a default policy, like our NVIDIA Agile trained policy, then of course, having more compute, having better compute, faster tensor cores, all the stuff and all the amazing goodness that makes Thor an upgrade, all those upgraded features help improve the performance of running that lower body control model. Yeah.
Okay, another question. I think will be the last one. The other question we didn't have time to reply. We will reply on Discord later. But meanwhile, this is the last question. Is on YouTube as well from Utarasa1821. Can you comment on integrating video game joystick on ROS environments?
Yeah, certainly. So I think what I'll say is that for many, many common video game joysticks, for example, I think the PS4 controller is one of the classic ones. Those controllers already have ROS support. And so, in fact, these are not Isaac ROS packages. These are open source ROS packages that other developers have built and contributed. And those packages can very easily translate the physical input, the physical joysticks, the physical buttons on the PS4 controller, and convert them into a ROS message on a ROS topic that a separate robot stack like NVIDIA's Isaac ROS stack can consume. So I would say it's actually very easy to do that. In fact, if you look online, you can probably find a solution for this. It's already out there from our amazing community of open source developers.
Well, thank you. Well, there are many other questions really running right now. Maybe another one just to share.
Okay.
Let me bring this one. Yes, from the same user. Can you share a quick summary of changes to enable Teleop and ROS 2 from different locations. This is time for Javier. Was in the same room as the robot.
Do you want to talk about this?
Yeah, for sure. So roughly, you have a couple of different options. We have actually done teleoperation where the teleoperator was in a different room of the robot. This isn't something we have advertised too much quite yet. But roughly, if I remember correctly, what we did was we ran the network on the robot, and then roughly they were on the same, like the headset and the robot were on the same network still. And then the teleoperator was in a different room, and then he was looking at cameras to see what the robot was doing. And then after that, I believe part of the stack was running on x86, specifically for the teleoperation part, and then the other half of the stack was running on the Thor. But we don't advertise this too much, but it is possible to do.
I'll mention, as somebody who was just recently teleoperating the robot, one of the challenges with having the human be further away is that you lose some of the sense of understanding of what the robot's doing. And so being close to the robot, being able to see through the headset what my perspective is as a teleoperator, and also have really low latency between where I'm sitting and where the robot's going to actually actuate. All those factors make it easier to get good data teleoperation-wise. But of course, if you are willing to tolerate a bit higher latency rather, and a bit less spatial awareness, then a distributed system could make more sense as well. Yeah.
Thank you very much for this question. Unfortunately, the time is flying. Thank you, Kajan and Javier, for this amazing office hour. And I would like to see news and updates for the soon. Maybe I will keep you updated for the next office hours. And now I would like to speak really quickly for the next GDC. Maybe I want to use an old question I see on the chat about where is Edmar? Edmar was at the GDC Taipei, and maybe if you didn't see the GDC Taipei, you can use this QR code to watch what Jensen say recently in the GDC keynote. Also follow all news we provide recently on the last GDC. We have also another link, I think so. Yes, for the physical AI announcement. Please use this QR code to read everything related for the physical AI announcement. And please, if you can jump, yes, for the next QR code, where NVIDIA enables the next era of physical AI research with agent skills for AV, robotics, and vision AI. Other important QR code with the links for everything related. And also for the NVIDIA research unlocks advanced grasping, smarter autonomous driving, and agent training at scale. This is another link for everybody can follow and know more. And let's jump for the last community resources. Like I say, all question that maybe you want to know now, maybe you see this recorded live, you can post your question on our forums on Discord. Also, you can watch our events, and this is the list of all events links from the forum and Discord available, and from the ambassadors. And I think is enough. If I remember well, I shared all links for all community. And thank you again, Kajan and Javier, for this amazing office hour. And see you next week. See you guys.
Yeah.
Let's see.